I have a hard partial pressures problem here for you from someone's textbook. In this problem, they give us a chemical reaction, molecular iodine making atomic iodine. Notice that the moles of gas increase in the products. Every time I start with 1 mole of gas, when the reaction happens, I get 2 moles of gas. So there's an increase in atoms of gas, or there's an increase of particles of gas. They've also given us the final pressure of the vessel. What does this mean? Well, this means that every time the reaction happens, the pressure increases, of course, because there are more particles of gas. So, there's the vessel, and here are some iodine molecules, and they are exerting some pressure, which we don't know. Every time the reaction happens, some of those iodine molecules disappear and become iodine atoms. A pair of them. Notice that now there used to be 1, 2, 3, 4. There used to be 5 particles total in this vessel, but now there are 1, 2, 3, 4, 5, 6. Now there are 7 particles total in this vessel. So that increase in the number of particles increases the pressure. Why are we so concerned about pressure? Because that's all they've given us to measure how much stuff is inside this vessel at the end of the reaction. So, we are measuring the amount of stuff in the vessel using pressure. We have the amount of stuff after the reaction, but we don't have the amount of stuff before the reaction. Let's get the amount of stuff before the reaction. We're going to be using pressure because they used pressure, and we need to compare the before and after pictures in order to figure out the mole fractions. Mole fractions, which is what they want. So, PV equals nRT. The pressure that we start with is equal to P nRT over V by dividing both sides by V. We know R. We know T. That's given right there. We know V. That's given right there. What about N? N is the moles of molecular iodine. The stuff that we have before the reaction occurs. The molecular iodine. Now that's given in mass over here. So let's convert that to moles. 42.189 grams of molecular iodine. On the periodic table, you multiply the iodine mass by 2, and you get that many grams per mole, and that gives us 0.16622 moles of iodine molecules. So that is equal to N. Yeah, it's just like a cooking show. I've prepared some of these numbers in advance. Not all of them. Right, so P equals, I'm going to start putting stuff in here now, 0.16622 moles times the gas constant. Okay, which gas constant do I use? Well, we're using atmospheres, and we're using liters. So I use a liters atmospheres per mole per Kelvin gas constant. All the gas constants are the same, of course. It's just when the units are different, you have to convert the gas constant also. Okay, so this new pressure is about 1.601 atmospheres. I can only have 4 significant figures. Why? Because that's 4 significant figures. That's 4. Oh, wow. I only have 3 significant figures in my gas constant. That's not right. I need to use the gas constant with more significant figures. It is really 0.08208, I think. So let's do that. It's not going to make a big difference, but just to be a little more legal. Excuse me. Okay, let's see how much difference it actually makes. 0.16622 times 0.08208 times 1173 divided by 10. 1.600. Oh, so it does make a difference. Well, not much of a difference. Atmospheres. Okay, now that is the pressure of the gas inside this container when it is only iodine gas. When it is only iodine gas. So before the reaction happened, when it is only molecular iodine in here, before any reaction happened, it is this pressure in there. Now, how do we figure out how much of this reaction occurred? Like how much of this there is at the end and how much of this there is at the end? Well, we'll use the chemical equation. And run the reaction in numbers. So, we start with 1.600 atmospheres. And we start, so this is the initial. I'm making a table here. This table is known as an ice table. Change equilibrium. This table is known as a equilibrium. This table is known as an ice table because initial starts with I, change starts with C, and equilibrium starts with E. That's why it's called an ice table. So the initial conditions are that we have 1.600 atmospheres of molecular iodine and 0 atmospheres of atomic iodine, because that's what those are the initial conditions before the reaction happened. Now, when the reaction happens, we lose a bit of this, and we produce a bit of this. But every time we produce this, we produce twice the amount of molecular iodine that we lost. And that's because there's a coefficient of 2 on the product, but a coefficient of the invisible 1 on the reactants. Now, how do we know that the reaction only went this way and didn't go backwards? Well, whether it went forwards or backwards doesn't really matter. What matters is what did it end up doing? What was the net effect? The net effect was forward a little bit. And how do we know that? We know that because the amount of stuff in here, in the container, was larger at the end than at the beginning, where at the end, the amount of stuff was 1.733 atmospheres. At the beginning, the amount of stuff was 1.600 atmospheres. So we know the net effect was a forward reaction. Now at equilibrium, which just means the end, I just take the sum of these things. So it's now 1.600 minus x. That's the sum of the initial and the change. And the sum of the initial and the change in the products is just 2x. So at equilibrium, at the end of the reaction, inside this container, inside this container here, we're going to have a bunch of these iodine molecules and a bunch of iodine atoms. And a bunch of iodine atoms. And we don't know how much of each. However, we do know that this bunch of molecules and this bunch of atoms sum up together to make 1.733 atmospheres. That's what we know. Right? So, taking the equilibrium line from my little ice table there, I'm going to add everything up. 1.600 minus x, that was the reactant side, and that's represented by these molecules in my drawing, plus 2x, and that was the product side, which is represented by these dots in my drawing, equals 1.733 atmospheres. Okay? 1.733 atmospheres. Okay, how can I just do that? This equation looks so easy. This equation, just simplified algebraically, is just 1.6 plus x equals 1.733. Why is that legal? It's legal because of Dalton's law of partial pressures. You know that in the container, at the end of the reaction, you have some leftover iodine gas, and you have a bunch of iodine atoms. Well, the partial pressure exerted by the iodine gas, which is the reactant side, plus the partial pressure exerted by the other gas in the container, which is the atomic iodine, the product side, equals the total pressure. That's Dalton's law of partial pressure. So that means I can just add these things up and get 1.733. So that's why this problem is so, well, it's supposed to be so hard. Let's see now. I'm just going to solve for x here. Should I do it in a different color so you don't get confused? Alright, I'm going to just solve for x here, where x is going to be 1.733 minus 1.6. So that's 0.1330. Alright, so the x is 0.1330. Alright, so what is that in units? That's atmospheres, because Dalton's law of partial pressure is all pressure units. Alright. What does this mean if x is 0.1330? Well, let me make some space here, and you can figure this out with me. So, if x is 0.1330 atmospheres, then that just means that the pressure, the partial pressure of I2 is 1.600 minus 0.1330. So the pressure, partial pressure of iodine, molecular iodine, is 1.600 minus x, which is 1.600 minus 0.1330. And this is in atmospheres. And so that is that is 1.467. That is 1.467 atmospheres. You should do this on your calculator too, if you're following along. Now the pressure of the products, which is just atomic iodine, is 2x. And that is 2 times 2 times 0.1330 atmospheres, which is 0.2660 atmospheres. Okay? So now we have the partial pressure of each component, and they want the mole fraction of each component. So remember, at this point you can just stop the video. I think you already know what's going to happen next. But if not, here you are. Now remember that the pressure of some gas is equal to the mole fraction of that gas times the total pressure. That's a consequence of Dalton's law of partial pressures. So, the partial pressure of the molecular iodine is equal to the mole fraction of molecular iodine times the total pressure. We know the total pressure. It was 1.733. And we know the partial pressure of molecular iodine. It was 1.467. So we can solve for the mole fraction of molecular iodine. And we'll do the same for atomic iodine. So, I'll do it now, and you don't have to watch if you don't want, or you can watch if you want. I'll do this in green. So, I'll just solve this equation first for the mole fraction. So, dividing both sides by the total pressure gives me the mole fraction. Alright, so the mole fraction of iodine is the partial pressure, 1.467 atmospheres, over the total pressure, 1.733 atmospheres, and that's just 0.8465. That's the mole fraction of molecular iodine, 0.8465. And the mole fraction of atomic iodine, I could figure it out using the same method, or alternatively, if you're feeling lucky or whatever, you can just subtract the mole fraction of molecular iodine from 1, 0.1535. Because if the mixture only has 2 gases, of course, the mole fractions must add up to 1, or 100%. So, I could just do 1 minus one of them, and I'll get the other one. That's it. It wasn't so hard after all, just a little tricky. How do you turn off this video? Oh yes.